machine learning session. I'm Satnam Singh, and it's my pleasure to welcome Timothy here, who's going to give a presentation, ChopChop, a programmable framework for semantically constraining the output of language models.
Is my microphone on? Can everyone hear me? Oh, can you turn on the microphone? Can everyone hear me now? Is it working? Yes? OK, great. OK, so I'll start. OK, so I'm Timothy. I'm presenting our paper ChopChop, which is about semantically constraining language models. And this was joint work done with all of these great people at UCSD. OK, so what is this talk about? So this talk is about how we can enforce formal specifications in LLM-generated code. So let's say that we have some programmer, let's say Alice, and Alice is using one of these coding LLMs to help her write some code. But Alice also has some kind of formal specification in mind. This could be like a variety of things. It could be expressed in a program logic. Maybe it's a specific type signature, or it's like some static analysis that the program that the LLM returns should satisfy. But regardless of what the specification is, right, how can Alice get a guarantee that the program that the LLM returns satisfies the spec she has in mind? So in this talk, I'm going to show you our framework for constraining LLMs to return code that only satisfies specifications. And the key thing to note is that I'm using the word framework here. And that's because our method is parametric over an encoding of your specification. So that means that you can encode whatever type of specification you want in our system. And so for this paper, we used two different case studies that are specific instantiations of our framework. So I'll talk about these later, but the first one is we constrain the LLMs with some kind of equivalence constraint to a reference program using egraphs. And in the second case study, we constrain LLMs with respect to type safety for a subset of TypeScript. But you might be wondering, so what is the point of this framework in the first place, right? Why do we need a framework for this? Because there's sort of like an obvious solution that you could use to ensure that the output of the LLM satisfies a formal specification. And that's basically just to hook up the LLM and a verifier in a loop, right? So this naive approach is called rejection sampling. And basically, you just ask the LLM to generate a whole program. You put it into a verifier. If the verifier says yes, we can just return it to Alice, no problem. And if it doesn't, we can reprompt or retry with the LLM. And keep on doing this a couple of times, and hopefully eventually we get something that works, right? But there's sort of an obvious problem with this, right? Which is that this might take many iterations. And maybe the underlying issue is that we're not giving the LLM any feedback until it's generated the whole program. So first of all, this cycle might not even terminate if the LLM sort of spins its wheels forever. And it's also computationally inefficient. And so in some sense, what we're really not doing here is maximizing the value of our specification, because ideally we would like to use the specification to inform the generation process, right? In this kind of naive rejection sampling approach, the specification isn't being used until we've generated the whole program. So to sort of fix this issue, people have come up with this idea called constrained decoding. And so I'm just going to explain this idea with a simple illustration toy constraint. So let's say that we're asking a LLM to generate a Python signature. So just a bit of background on how LLMs work. If the LLM has generated some text, like maybe def, internally how LLMs work is they'll maintain a probability distribution over which tokens can come next. So maybe this is foo, AB, open parentheses, and 1. And normally, the LLM is just going to sample from this distribution sort of willy-nilly. It's going to be able to pick any of these tokens. But the idea of constrained decoding is that we're going to do some kind of analysis on each of these tokens. And so we're going to ask if we add each of these tokens to the text that we've generated so far, is this a prefix of something that satisfies our constraint, which in this case is being a valid Python function signature. And so we're basically going to maintain this invariant throughout the process that whatever text the LLM has generated is always a prefix of a valid program. And so in our example here, because Python function signatures can only start with identifiers after the def, and they can't start with numbers, we can remove these two tokens, and we'll stop the LLM from picking them. And like I said, we're going to keep on maintaining this invariant, and this process will continue for 2 or 3 more tokens until eventually, let's say that the LLM finishes something, and we get something that's correct by construction, because we've been maintaining this invariant the whole time. So, like the thing that we saw in that example is that like the core analysis that we need to do is to check if that the text the LM has generated is a prefix of some kind of valid program, right? And valid program there was like a very like basic constraint, like maybe you could enforce it with some kind of like regular expression or something. But in the examples I mentioned earlier in the talk, like with this egraphs and types thing, like these are like sort of like much harder properties, right? So the question of this talk is how do we build these kinds of prefix analyses for these more expressive properties? So let's look at sort of like what the ideal interface that we'd want is. So if we have some kind of like abstracted formal specification phi, and we had some kind of checker like p models phi, what I want is I just want to like input this checker, and then I want to magically, like through some black box process, derive a constraint decoder, which again is just doing this prefix analysis idea of checking if a prefix omega has a completion satisfying phi, right? And so this is what we would like in theory, and there's sort of some limitations of existing constraint decoding strategies that do not really realize this picture. So in particular, there's sort of like two classes of current approaches to constraint decoding. One is grammar constrained, and two is handwritten constraint decoders. So let's look at how these approaches sort of fail to meet this ideal picture. So in grammar constrained decoding, we restrict the class of constraint to specifically be about context-free grammars. So this means that we can only talk about things involving like syntax. So the good thing about this is that you can sort of just input an arbitrary context-free grammar, and it's very like configurable. You can change the grammar however you want. But the bad thing is that for those properties that we mentioned earlier in the talk, like egraphs and types, those are not like context-free languages. They're not like really syntactic properties. And so we can't really use this if Alice wants like type-safe programs or something, for example, right? And it's worth noting that this grammar constrained decoding is used in industry a lot. So if you know the name like structured outputs, this is like really grammar constrained decoding under the hood. And it's being like used now by big companies like OpenAI, Google, and Anthropic. So if we want to have these more expressive constraints like type safety and like egraphs and so on, another option is we could just manually implement the constraint decoder ourselves. And some existing work has done this as well. And so the idea here is that we'll fix a specific phi, and we'll just like manually like think really hard and come up with some constraint decoder implementation for phi. And so like some papers have done this, like I said. So there's this paper from PLDI last year that did it for type checking. There's this paper from NeurIPS a couple years ago that did it with some simple static analyses. But the problem here is that we had to be like very manual and very deliberate in crafting this thing. Like if we want to like program the constraint, it's not like the easiest thing to come up with, because as we'll see in a second, it's like not actually that trivial to like program these kinds of analyses like by hand, and it's like very nasty to think about. And so what we're left with is like this like really unsatisfying picture, right? So there, if you can kind of imagine like two axes of constraint decoding. So one axis of like desirability is programmability. Like can we change the constraint and like have some kind of like parametric interface? And the grammar constraint stuff is like great for that, because a context-free grammar is sort of like a nice declarative specification that we can use as like a parameter to build a constraint decoder for us. And the flip side is that the handwritten stuff can do like very expressive kinds of constraints like type safety, but people have to come up with the constraint decoders themselves in like a very manual fashion. So this paper is aimed at sort of being the best of both worlds and being in this like top right corner here, and that's we're trying to be both programmable and expressive, and that's what I'm going to show you today. So how do we accomplish this, right? So the idea is that we are going to provide like almost a minimal interface and then derive the constraint decoder for you. So concretely, to use our framework, users are going to provide two inputs. So the first input is just a grammar-like thing defining the syntax of the language. So if you used a tool like Yak or something before, it's like very similar to this, and it's basically just defining the concrete syntax of the language. And then the other thing that users have to provide is a encoding of the constraint. So in the slide title, I say almost for free, because ideally, the user would just provide the definition of their specification, and we would somehow derive the constraint decoder automatically. But we have this like almost parenthetical, because what they're actually going to provide is a lifting of the constraint. And the idea is that it's going to borrow from the sort of classical idea in program synthesis of like pruning. And what this is going to encode is how the constraint acts on sets of programs. So the idea is that given a set of programs, it's going to return some subset of constraint satisfying ones. And I'll talk more about like how this like concretely looks like in a little bit of a second. And so our approach really has like two core ideas, and I'm going to walk through this first idea of constraining strings through prefix spaces. And we're going to see how these inputs can be used in our approach to build a constraint decoder automatically. So let's like think about why constraint decoding is like hard to implement manually first. So let's say that S is a string, and I am in some language where, for example, it is ill-typed to add integers and strings. So let's imagine that we're writing a constraint decoder that enforces some kind of like type-safe invariant, and we're asking the question, is 1 plus s a prefix of a well-typed program? Now you might say, OK, I know the answer to this, right? We can't add ints and strings, so like the answer should be no. But as a complete program, like this is like kind of like like the picture that we have in mind. But in reality, like what if we had like a .length method on like strings, for example, right? Then there actually is a well-typed program completion in this example. And it's like very tricky, right? It's like not like intuitive that like this is the case. So like what went wrong with like sort of like the naive style of reasoning here, right? So the issue is that if you want to implement a constraint decoder, which is analyzing strings, you have to explicitly reason about things involving the concrete syntax of the language. And this includes things like what operators there are in the language, their precedence, whether the language has like left recursion, how strings lex, and so on and so forth, right? And all this stuff is like really nasty to think about manually, right? Like we don't intuitively want to have to like think about this, right? Sort of like if Alice is trying to implement her own constraint decoder, the picture she has in her head is probably something like this typing rule on the right, which is saying that numbers, like addition is well typed if like the left and the right hand side are both like numbers, right? Like this is like very like beautiful and like simple. We don't want to have to worry about like the like method syntax for a language, right? Like this would be like horrible to like program manually. And existing approaches had to kind of like bake that in and like think really hard about the specific concrete syntax of their language. So the idea of our paper is that we are going to avoid all of this. And the way that we're going to avoid it is with this abstraction called a prefix space. So the intuitive idea is extremely simple. So a prefix space is just going to represent the set of all abstract syntax trees corresponding to programs starting with a prefix. So as an example, let's say that our prefix is 1 plus s. Then the prefix space for 1 plus s is going to be an infinite set. And it might contain trees like 1 plus s, 1 plus s plus 2, or 1 plus s times 2. And notice that these are all parses of programs that start with 1 plus x, if you think about them like as text. And I want to pay specific attention to that third example here, because we can see that like based on like how things parse, the abstract syntax trees that we represent in the space, the nodes might not like sort of be connected when you think about what's in the prefix and what's not. Like there might be some like distance between like the plus and the s, for example. And so it's like a little like strange to think about. And like this is like the core idea behind like abstracting away these like nasty details about concrete syntax. OK, and so the idea is that first we're going to build this prefix space. And when we build this prefix space, we're going to get some like space that represents like all of these programs and like infinitely many more. And we are going to take our pruning function that I mentioned was an input to our system. And what the pruning function is going to do is it's going to take this entire space and shrink it to some subspace of programs that approximates the set of constraint satisfying ones. And then we're going to ask, is this like shrunk subspace empty? And so if it is empty, that means that there is no program in the prefix space that satisfies our constraint according to our pruning function. And so we are going to say that the prefix is invalid. If this set is not empty, that means that there must be some program in this prefix space like satisfying the constraint according to the pruning function. And so we can say that the prefix is valid. And so to summarize, this is sort of like the formulation of like when we accept a prefix or not. So we're asking an existential question. So does there exist a program in the prefix space so that the program satisfies the specification? And I want to take special attention here to the structure of this formula, because if you're familiar with some like classical synthesis ideas, for example, like SIGIS or like realizability, you might recognize that like this is like sort of the classic setup for a synthesis problem. And we're going to see that this is going to allow us to like leverage some insights from synthesis into building constrained decoders as well. Okay, and so now that I've shown you the sort of the high-level sketch of our approach, the next thing I'm going to talk about is how users actually program this like pruning function and what the interface of the system like looks like. And our second core idea for this paper is that you can program over spaces of programs using co-induction. So the idea is that basically we're going to define an algebraic data type representing spaces of programs. So in the slide here, we've defined an ADT, and it says that a space is either empty, a union of spaces, might be a constant integer, a variable string, or it's an addition of two spaces. And so you can think of this as like an ADT for the abstract syntax of the language, but sort of just souped up with these additional like empty and union constructors. And I mentioned that we're going to use co-induction. So the key idea is that we want to be able to represent infinite spaces of programs. And co-induction is going to be a programming formalism that allows us to manipulate and construct these infinite spaces of programs. So in the example on the slide here, we defined an infinite space S. And what this definition is saying is that S is a union of the space consisting of just one and all the programs that involve X plus some program in S. So S is recursively referring to itself, which is why it's an example of a coterm. And if you're a synthesis expert, you might recognize this as like being very similar to, for example, like a version space algebra. And so the idea is that this is going to give us a great abstraction for implementing our pruners. And if Alice has this like simple typing rule in mind, there's sort of like a natural formulation using our framework of how we write the pruners. So because these spaces of programs are are elements of a co-inductive type, the pruners are dually going to be co-recursive functions which act on these infinite spaces. And the nice thing is that this is sort of abstracted away from the programmer. So the implementation of the pruners is like more or less like similar to how you would write like a sort of like an ordinary type checker. That's just like doing some like pattern matching on like the cases of like abstract syntax trees or whatever. And we're just going to like get like this nice programmatic interface for free. Okay, so let's talk about the evaluation for our paper. So like I said in the beginning, we do two case studies. So in the first case study, what we do is we ask the LM to refactor simple expressions into equivalent ones. And this is like for like a toy functional language. So for example, like if we have this like distance formula on the screen here, like a valid output the LM could return is like this refactored version with like let bindings. And I say equivalent here, right? So like what does equivalent mean? So equivalence has to be like formally defined somehow. And so the idea is that we are going to use this data structure called a egraph. And we don't have time to discuss like the ins and outs of like how egraphs work. But you can just imagine that it's some data structure for representing equivalence classes of programs. And the equivalences are defined with respect to some set of rewrite rules that the user provides. So maybe this is like commutativity of addition, or the fact that like multiplication distributes over addition. So the basic idea is that we're just going to define some egraph, and then our method is going to be parametric in the egraph. So the pruner is going to take an egraph as an argument, and then return a function on spaces. And the idea is that we're just going to look at the equivalence class for the source program that we started with. And to implement the pruning, we're just going to intersect it with the prefix space that we have when we're doing the constrained decoding. And if you're like an expert on egraphs, you might know that a egraph conceptually represents a regular tree language, which is why we are able to do this intersection exactly. Okay, and then the second case study, we just do like some like simple like TypeScript benchmarks. So these are like collections of like simple tasks. So like in this example, we're trying to find like the like next perfect square, and the constraint that we're enforcing here is basically just type safety. So we want the LM to output like well-typed TypeScript functions. Okay, and Before we talk about the results, it's important to note that we have this great guarantee from our framework, which is that with semantic constrained decoding, we will never generate an invalid program because, like by construction, we maintain the invariant that everything is a prefix of a valid program according to the constraint. But just because we don't generate invalid programs doesn't mean that we always generate valid programs, right? So in particular, our constrained decoding method can still fail if like the LM like gets stuck and keeps on like trying like bad tokens, or if it like runs out of like some like budget which we allowed it. So let's look at our results. So this is for code llama 13b, and we have more data in the paper. So if you want to like look at all of our like results, you can look in the paper for that. But you can see that across both benchmarks, we see like a general improvement with semantic constrained decoding, and this is compared to both grammar constrained and unconstrained baselines. So in the grammar constrained baseline, all we're doing is only enforcing that the LM generates something that's syntactically valid, which is a strictly weaker condition than our semantics constrained decoding. And then in the unconstrained, we're not doing any constrained decoding at all. And OK, in terms of future work, right now, there's like a little bit of issues with like scalability. So we're not running this on like the most like expensive hardware or anything, but we empirically see about like a 2 to 3 times like slowdown when we use our approach compared to running the LM unconstrained. We're interested in making these like pruners easier to program. And then like the last thing I want to mention is that in this talk, the way that we did constrained decoding is sort of parametric over a pruning strategy. And the great thing is that program synthesis has been around for 30 years, and we have like studied all these kinds of different domain-specific pruning techniques in synthesis. So in some sense, our paper can sort of be lifted with one of these techniques to like build constrained decoders for free using like any like pruning strategy from like classical synthesis. And so we're really excited about this. So like if you have some like application in mind and you work on like such a pruning technique, please come talk to us. OK, so this is the summary of the paper. That's all. Any questions?
Thank you very much, Timothy.
OK, let me, I can ask 2 questions if there is time. OK, so first I will start with like the experimental setup. So you used code llama and not like the recent models like Cohen 3, so there has been like works on like issues found out like constant decoding actually harms performance for reasoning models. So did you observe something like that?
Sorry, I couldn't hear the last part. Can you say a little louder?
So there has been some works that says like the constant decoding actually harms like the task-specific performance for reasoning models and other.
Yeah. So this is a great question. So so there's been some like empirical papers that show that constrained decoding can like basically mess with the distribution of a LM. So the good thing about that is that it's sort of an orthogonal problem to our paper. So our lab has actually like studied like different like sampling strategies that sort of resolve those sorts of issues. And like basically the issue is that the constrained decoding can like steer the LM like out of its like probability distribution when we like remove some token choices. And like the way that people alleviate this is they like come up with like more sophisticated like sampling strategies about how to like pick tokens from the probability distribution. But those are still like using some kind of like prefix analysis that tells you whether or not a token is valid. And so like the question of like making the LM like sample more in distribution is actually like sort of like orthogonal to this paper. So like the short answer to your question is that like this is like a sort of like a like known issue and there's like known solutions, but I mean it's like a orthogonal problem basically to the paper.
So the second question is more theoretical side. So one problem with constant decoding is like the tokens that are generated by LLMs is not like the exact characters that defines like the formal language, like the alphabet, right?
Right.
The token misalignment problem. So one of the main problems is sometimes like how you ensure like soundness for like different tokenizers in like more problematic case, like when multiple tokens represents a single character. So is like does your framework suppose new tokenizers or?
Yes. So the question is basically the tokens the LLM outputs might not correspond to the like lexical tokens in the language. And yeah, like this is like a known problem. And the short answer is that when we're constructing the prefix spaces, we basically have to like take this into account and like do some kind of like analysis about which ways different tokens can lex. But we do support this in our framework. And like it's not a problem for us.
Let's take one more quick question.
Yeah,
Joey can set up that simultaneously.
I just have a quick question. In some settings, does this boil down to type inhabitability?
Yes.
And given that, I'm wondering your guarantee on slide 44. Like, how do you guarantee that in that setting?
Yes. This is a great question. So so we're asking if in some space of programs if there's like a well-typed term. So yeah, you can imagine it as like a type inhabitability like type formulation. And like you might know that like okay some of these like type inhabitability problems might not like be decidable if like the type system is like sufficiently expressive. So the answer that I like kind of skimmed over in the talk is that the pruning function is probably going to be approximate in some kind of sense. So like we have more details about this in the paper, but the like short answer is the user will encode some kind of approximation instead of like an exact like pruner. And then we still get like some like soundness guarantees even if like the user enforces like an approximation, but like more details can be found about that in the paper, I guess.
Let's thank Timothy for a great talk.